today's lecture about lead-acid batteries. The content of today's lecture you also find in the book Energiespeicher, Bedarf, Technologien, Integration that I had been writing together with my colleague Michael Sterner from OTH Regensburg and many other co-authors. Unfortunately, at the moment it is only available in German, but we already have translated it into English, and hopefully the Handbook of Energy Storage will be published and available in bookshops in a few weeks to a few months. When we go to the history of lead-acid batteries are maybe one of the oldest battery technology. And it was in 1859 when Gaston Blondet put two lead sheets together separated by a rubber stripe to show that this is an electrochemically working system. It was then in 1887 Henry Tudor who started the industrial production of lead-acid system. And in 1950 the company Sonnenschein had been the first who went from the liquid electrolyte to the so-called dry cell batteries with a chilled electrolyte. And today, in the year 2000s, the modern lead-acid battery is the most commonly form of battery storage apart from the so-called small cylindric consumer batteries. So apart from all the hype on lithium technologies nowadays, please don't forget that the lead-acid batteries still have their role. Don't ignore them, they might become angry. So where do we find nowadays the applications for lead-acid batteries? First we have the mobile applications. Everybody of us has them in their cars as a starter battery, but they are also used as traction batteries in forklifts, for example, and in stationary storage systems. That is what we are looking here for renewable energy systems, to balance generation from solar and wind systems, or we find them in big battery rooms in emergency power supply systems. We can distinguish from a construction point of view the flooded batteries and the sealed batteries. The flooded batteries, the older ones, they have the electrolyte H2SO4, sulfuric acid with water, and there it can be that there is a gas exchange with the environment. So when oxygen and hydrogen are released, we have a loss also in the water level. They have low maintenance, but they have maintenance, and occasionally we need to refill water. Whereas the sealed batteries, the electrolyte is still sulfuric acid, but here the electrolyte is bound in a gel or in a fleece, and they have a pressure relief valve that opens at high pressure within the cells. Normally that should not be opened, but whenever we have a wrong battery management and also here gases are produced, then they are released here, and they are called maintenance free. What we see here on that slide is the construction of an absorbent glass mat AGM battery from Hoppeke, and we see in the container many components. We have a big set of positive plates and negative plates, and they are separated by a fleece, the separator, and then many of those packages are packed together to the plate groups, and then they are fixed together that from outside we can connect the battery with the positive and the negative pole. And of course we have the valve plugs for gases to escape in case of emergency. Once we have opened the lead-acid battery by force to look how it looks inside, and there again we see the positive plate followed by a negative plate separated by this orange paper looking like separator. You see the bar connecting all the positive and the negative plates. The two connections for the positive and negative on top of the battery, and also the vent plug. The electrodes can be fabricated in different types. So first of all we have the large surface electrodes. They are only in a battery system. The positive electrode is made out of that. They have robust long lifetime, not in terms of cycles, there is maybe only 200, but in terms of years, and it's typically applied in power stations. Then we have the flat plate, where the positive and negative electrode is made of a flat plate. They have a short discharge time and a high discharge current. They have a lifetime of up to 300 cycles and typically applied in starter batteries or emergency power supplies. And finally we have the tubular plate, where the positive electrode is made as the tubular plate, whereas the negative again is a flat plate. They have long discharge times at low discharge currents, and they can reach up to 2000 cycles and typically applied in what we are looking for here in solar systems, in renewable systems, in traction applications. So when we have a closer look to the charging and discharging reactions, we have in the plastic container the negative plate made of lead, the positive plate made of lead dioxide. In between we have the liquid, the H2SO4 mixed with water and the separator in between. When we now connect the two plates via electric consumer, then we have the discharge reaction. That means on the negative plate, out of the lead with sulfuric acid, we have formed the lead sulfate, and the same happens also on the positive plate. That means we have 1 part lead, 1 part lead dioxide and 2 parts of sulfuric acid, and that is formed 2 parts of lead sulfate and 2 parts of water. The good thing is that this reaction is reversible. That means when we now connect the power source to the battery and we have electric charges produced, we have a reversible reaction, meaning we have the 2 parts of lead sulfate with the 2 parts of water, and they react back again to lead dioxide and 2 parts of sulfuric acid. Theoretically that would give an infinite lifetime, but unfortunately we also have some side reactions. And on the negative electrode we have the oxygen reduction and the hydrogen formation. And hydrogen is formed and we have a concentration of more than 4% in a closed room, then we have the danger of explosion. And that's the reason why we need to have ventilation in battery rooms. The reason for that is the corrosive generation of antimony. The oxygen reduction is of great importance more for the sealed batteries, because there we have a fast transportation in gas channels, which is not a big problem in the flooded batteries, because there we have a quite high resistance in the sulfuric acid. But finally we need ventilation. On the positive electrode we have the oxygen formation that is catalyzed by impurities like cobalt. In sealed batteries the oxygen diffuses to the negative electrode and the reaction with hydrogen leads to the generation again of explosive gases, why we need ventilation. So don't forget the ventilation, and it's a good idea not smoking in battery rooms. What else? We have the grid corrosion problem, the formation of lead dioxide corrosion layers. They increase the volume of the positive lattice, and then we have a release of antimony, and the antimony can contamine then the lattice. And what we will look now in the next video is the operation of lead acid batteries. Thank you very much.